Of all the planets in the solar system, Earth and Mars, the third and fourth planets from the Sun, are the most similar. But despite the similarities, Mars is essentially like no other planet. It is a unique world. It was an elusive and baffling planet to astronomers for hundreds of years. Through early telescopes, it appeared to be a small red sphere, later estimated to be about half the size of Earth. One of the earliest known representations of the planet, drawn in 1659, indicated markings on the surface. And by the movement of these dark patches across the disk, it was shown that Mars rotated on its axis in a period only a little longer than Earth's, about 24½ hours. It was observed, too, that the tilt of its axis, like the Earth's, exposes its polar regions alternately to the sunlight. Thus, each hemisphere has a summer and winter period. And since Mars orbits the Sun in 687 Earth days, one Martian year in each of its seasons is almost twice as long as Earth's. Later mappings of the planet displayed light and dark regions identified erroneously as continents and oceans. The land masses red as the sandstone districts on Earth, the water a greenish blue. In 1877, an Italian astronomer, Giovanni Schiaparelli, discovered what he called canali, or channels, resembling, he said, the finest threads of a spider's web drawn across the disk. In America, Percival Lowell founded an observatory to study these Martian features. Massive irrigation systems, he called them, designed to carry water from the melting ice caps to the major centers of a dying civilization. Science fiction writers populated the cities with terrible creatures of heroic size, with skills beyond Earthman's dreams. In the 1960s, 3 Mariner spacecraft flew by Mars and photographed about 10% of the surface. Gone were the canals, gone were the cities, gone the brilliant and sinister Martians. The photographs revealed a cratered landscape much like the moon, waterless and apparently hostile to life. But in 1971, the Mariner 9 spacecraft orbited Mars and transmitted more than 7,000 photographs of the planet to Earth. The extensive mapping revealed a new and unexpected world. The southern hemisphere, seen by earlier spacecraft, flattened and gouged by the impact of meteorites. The northern hemisphere, a vast plain with few craters. And rising from the plain, a great dome called Tharsis, topped by giant volcanoes. The plateau that joins the two hemispheres is cut by a vast and deep canyon, and by channels with the characteristic patterns of stream beds on Earth. Some of the channels suggested that water may once have flowed on Mars, and thus life might have evolved and possibly adapted to Mars' changing conditions. And then in 1975, 2 Viking spacecraft were launched, each of which was programmed to land a robot on the Martian surface. One of its principal objectives was to test for the presence or absence of living organisms. A communication system linked the spacecraft to the Mission Control and Computing Center in Pasadena, California. On June 19, 1976, the first Viking arrived in the vicinity of Mars after a year-long journey of more than 400 million miles. Once in orbit, its cameras were turned to a detailed examination of the landing area. Imaging teams on Earth scanned some 800 photographs covering a territory about the size of Texas. The chosen landing site was a flat expanse with a few impact craters, one of the lowest regions on the surface. On July 20th, 1976, flight controllers ordered the lander to separate from the orbiter.
5, 4, 3, 2, 1, separation. Descent sequencing, we're at mission event word 0, and we have DL separation.
Because of Mars' great distance from Earth, the signal traveling at the speed of light, 186,000 miles per second, took 19 minutes to reach the spacecraft. This necessitated a completely automated system on board for carrying out the landing maneuver. During the lander's descent, its instruments analyzed the properties of the thin Martian atmosphere.
9,000 feet coming up on quarter bar pretty soon.
Good roll attitude hold.
Getting close to quarter bar. Firm quarter bar. Two loops and a high. Got it. We have quarter bar. Lander confirmed parachute deploy. Recon 1, TM2. Do I have sync? UHF minus 105. Format 3 is in sync. All right. Format 3 in sync. Leg deploy. 4,800 feet, 177 feet per second.
Confirm roll maneuver.
Parachute separation. Roger. Minus 105.
23 Gs.
2,600 feet, 188 feet per second.
2,600 feet. 2,600 feet.
366 feet, 73 feet per second.
ACS is close to vertical.
Nav is green for touchdown.
ACS is green, 1.5 degrees per second max, 0.2 Gs.
6 feet per second.
Touchdown, Win. Fantastic. 16 kilobits confirmed. Yes, we have a touchdown time of 12 hours, 12 minutes, 07.1 seconds.
A job very well done. Outstanding, great, navigation, perfect. I'm assuming that we must be sitting right on the X. So that's the smooth area. So everybody just did fabulous and couldn't be more pleased. Thank you.
25 seconds after landing, one of the two cameras was initiated and scanned the first picture of the Martian surface.
About a half an hour later, when it started to come back from the orbiter, and we got the first 7 lines on the TV monitors, you could see gray and white light levels, and we knew there was something there. Look at the beautiful rock. Fantastic. And all of a sudden, we were looking at the surface of Mars, and it was clear, it wasn't dusty, it was sharp. And when we got to the end of that first picture, with the dust and small pebbles in the footpad, it was just, it was really a miracle.
In an instant, the picture was wiped off the TV monitors, and behind it came the filling in of the second picture, a long panoramic view that covers 300 degrees and extends from the lander to the horizon. It disclosed a sector of the basin called Chrysoplanitia, covered with sand or dust and littered with rocks. The following day, Viking sent back the first color picture. A fine dust, red or yellow-brown, covers the ground. The sky is a light tint of the same color due to the particles of dust suspended in the air. 45 days after these historic events, Viking 2 landed in an area 4,600 miles northwest of Viking 1's landing site. A vast plain, littered too with rocks resembling those on Earth, produced by volcanic processes or by meteorite impact. While the landers conducted experiments on the surface, the orbiters swinging around the planet measured variations in moisture and temperature and took high-resolution photographs of the Martian terrain. Four and a half billion years ago, the planets were formed from the gas and dust of the solar nebula. In the formation of a planet, heat is released and remains embedded in the growing mass. Because the heat can't escape as rapidly as the mass is growing, a point is reached eventually where the interior melts. On Mars, the heavier material sank toward the center, and the lighter material rose to form a crust at the surface. And this crust contained ice and other condensates. A later stage may have occurred where molten rock intruded into the crust and melted the ice, causing a slurry of water and rock and dust to flow across the surface. Some observers believe that such a process may have been the cause of the major channels which we see on the surface of Mars today. But others believe that in Mars' first billion years, the atmosphere may have been warm and dense enough for rain to fall and for rivers to flow. Gradually, the original thick, wet, and warm blanket of the atmosphere evolved into the thin, dry carbon dioxide atmosphere we find there today. Because of Mars' low atmospheric pressure and low temperatures, water can't exist in liquid form. It must either freeze or evaporate. But while there are no oceans or rivers on Mars, there is more water in total than anyone had expected. The residual polar cap in the north, which remains after the hottest part of the northern summer, is water ice mixed with dust. And the measurements of the seasonal behavior of water vapor over the planet suggest that there is a vast reservoir of ice beneath the surface, so that one can think of the residual polar cap as the tip of an iceberg protruding from a sea of rock. At lower latitudes, the water vapor condenses to form clouds that ride high in the atmosphere or swirl around the slopes of Martian volcanoes. And further south, in the canyons and valleys, there is frequently an ice haze seen to form and evaporate in the early hours of the morning as the sun warms the atmosphere. On Earth, the ocean's heat and moisture and the heat and air currents over land masses interact to produce complex weather patterns. On Mars, because of the absence of large bodies of water and of massive cloud covers, the weather doesn't vary much from day to day. Like a remote weather station on Earth, Viking's meteorology instrument measures Mars' atmospheric pressure, temperature, wind speed, and wind direction. Temperatures range from minus 122 degrees Fahrenheit just after dawn to minus 22 degrees in the mid-afternoon. Light winds from the east in the late afternoon change to light winds from the southwest after midnight. Maximum wind speed is 15 miles per hour. But in the early summer, the heating of dust particles in the air generates violent dust storms in the low regions of the planet. Driven by winds that reach 150 miles an hour, they may blanket the entire planet in a few days.
In order to understand the geology and physics of wind-blown particles on Mars, we're conducting a series of experiments using this enormous space environment chamber here at NASA's Ames Research Center. We've placed an open circuit wind tunnel in this chamber, and we're able to operate at atmospheric surface pressures comparable to those on Mars. In this particular series of experiments, we have placed a crater model in the tunnel floor, and we want to determine the zones of erosion and deposition around the crater. In this particular case, we're going to let the wind blow across the crater and see what those zones of erosion and deposition are like.
The light and dark streaks associated with craters are the most common features on the surface of Mars related to wind. The light streaks are deposits of fallout from the global dust storms. The dark streaks are regions from which a thin layer of light material has been removed revealing a darker underlying surface. These streaks serve as wind markers. Their patterns define the wind flow. To the geologist, the features seen in the tens of thousands of photographs transmitted by Viking are the visible signs of the enormous forces and processes that have shaped the surface of Mars. The excavation of large basins and craters by the impact of meteorites and asteroids. The raising of mountains by the action of volcanoes. The faulting and subsidence of the crust as the planet expanded. And the cutting of channels by water, or abrasive particles driven by winds over a period of tens of millions of years. The key to the age and sequence of these features is found in the number and condition of craters. Those areas with fewest craters are assumed to be the youngest. Here, a fresh crater overlies an ancient eroded one. Here, the rim of a crater is eroded by water or wind. And here, adjacent to a fresh crater, is one of a cluster of crater rings, craters that have been buried to varying depths. Over millions of years, the repeated flows of lava built the volcanic mountains of Mars. 12 are larger than any on Earth. The largest, Olympus Mons, rises 3 times higher than Mount Everest and is broad enough to cover the whole chain of volcanoes that form the Hawaiian Islands. The great gash that cuts through Mars' equatorial zone is Valles Marineris, a mighty canyon system that extends over an area more than 3,000 miles long and up to 400 miles wide, and drops 4 miles below the flat cratered surface of the plateau. Canyon walls are gullied, dissected by tributary canyons, or scarred by catastrophic landslides, leaving steep cliffs and great fractured surfaces. Extending for 30 miles on the canyon floor is a field of sand dunes, suggesting that some of the debris produced by the collapse of the canyon walls was removed by wind. These ancient channels that resemble dry riverbeds on Earth could have been formed by primeval rainstorms. But the vast channel systems that start in areas of collapsed terrain, with broad streamlines extending hundreds of miles across the lowlands, and teardrop-shaped islands soaring to thousands of feet above the channel bed, testify to a process without any parallel on Earth. Viking also photographed the 2 cratered moons of Mars, Phobos, the inner moon, marked by striations which, on closer view, resolve into grooves several miles long, and Deimos, the smaller outer moon. Viking, traveling at 3,800 miles an hour and passing only 30 miles away, could observe boulders on the moon's surface, some as large as 100 feet across. The geologic record of the planet suggests that Mars, like the Earth, has experienced periodic changes of climate. The best evidence of this is seen in the strange spiral patterns of Mars' polar regions. The dark bands are scarps or cliffs of bare ground within the North Polar ice cap. On each scarp are numerous small terraces eroded from layered rocks. This is a model of layered terrain, an area about 40 miles across. It is believed that the large scarps and the small terraces represent 2 different cycles of climatic change which occurs simultaneously. Because of Mars' oscillation in its orbit about the sun, the polar regions are alternately warm and cold for periods of tens of thousands to millions of years. During the cold period, mixtures of dust and ice were deposited in a series of near horizontal layers, obscuring the underlying topography. Then a period of warmer climate followed, and erosion set in, cutting deep valleys into the icy mass of the polar caps. After the erosion cycle, new layers were laid down, and another episode of erosion followed. This oblique truncating of one set of terraces by another indicates that the climate turns on and off, the first geological evidence for cyclical climatic change on a planet other than the Earth. The speculations about changes in the atmosphere and climate were closely related to the notion that life in some form might exist on Mars. On Earth, life developed several billion years ago, at a time when the overall properties of Mars and the Earth were very similar.
Now, over the ensuing billions of years, Mars and the Earth evolved separately. However, Mars today still has chemicals on its surface, an atmosphere, temperatures and pressures within which we believe life can exist. The Viking lander was equipped with 3 life detection experiments designed to test for chemical changes caused by life processes that are familiar to us on Earth. On Earth, all living organisms interact with the environment through a process called metabolism.
Animals, for example, take oxygen from the environment and use it to combust food, thereby obtaining energy. At the same time, they release carbon dioxide and other waste products into the environment. Green plants and some microorganisms do the reverse in the process of photosynthesis. They remove carbon dioxide from the environment, and using sunlight as the energy source, they convert the carbon dioxide into organic matter and release oxygen into the environment.
If the experiments on Mars indicated that similar processes were occurring, then we would presume the possible existence of organisms on that planet. Well, our results on Mars in certain experiments gave us data that seemed to mimic the metabolism of living organisms. However, careful analysis of that data indicates that it is probably the result of chemical rather than biological processes.
On Earth, all biological systems are based on organic chemistry, and it was believed that life on Mars would also be based on organic compounds. The notion was strengthened when experiments on Earth demonstrated that organic materials can be formed under simulated Martian conditions.
We used finely powdered minerals like those expected on the Martian surface. Then we added traces of water vapor and radioactive carbon monoxide at low pressure. To simulate Martian sunlight, we irradiated the mixture with light from a xenon arc lamp. When we heated the sample and captured the gases that were formed, our radiation counter showed that the carbon monoxide and water had been converted to organic compounds.
But Viking's instruments failed to detect organic compounds of any kind. That fact, in the opinion of some observers, has increased the odds against the existence of living organisms on Mars.
If we were able to do 1,000 experiments, different experiments on Mars, and to do these in a wide variety of places on Mars, in the canyons, on the polar caps, in some deep areas of the surface, and if in all of these experiments we got negative results, then the answer to the question, is there life on Mars, would almost certainly be no. But on the basis of just a few experiments, done at only 2 sites, very bland sites on the planet, I think it would be unscientific for us to come to that conclusion. All we can really say for sure is that we have run across some very interesting chemistry, a kind of chemistry that we do not see in surface samples from the Earth or surface samples from the Moon, and that's about where we are at the moment. Today, in laboratories across the nation, scientists are trying to simulate the results that we obtained on Mars. Some of the scientists are concentrating on irradiation experiments to see whether solar energy acting on Mars could have produced chemicals to account for the results. Other experiments are assuming that these chemicals were there and are testing one or another of these chemicals to see whether they can account for the results that were obtained.
The question of life on Mars is only one of the inexhaustible number of questions for which we continue to seek answers in space. Questions about the origin and evolution of the solar system, of our own planet, and our own species. The search for answers is a goal of planetary exploration, and the journeys of our spacecraft to the near and far reaches of the solar system are beginning to provide some of the answers.